Okay, we're going to talk a little bit about nomenclature of alkanes. Again, this is more for general chem level. This is not if you're in second year organic chemistry, but it could certainly help if you need the basics. These rules come from the International Union of Applied Chemistry for Pure and Applied Chemistry, or IUPAC. You're going to find the longest chain and use that as the name of the compound based on our 10 hydrocarbons that we've learned so far. But make sure you find the longest chain. It's not always obvious. Number the carbon atoms start with the end closest to the substituent. Sometimes it won't matter, it'll be equidistant, and then give the name and location of each substituent. When there are two more substituents present, list them in alphabetical order. The substituents are the groups attached to the longest chain. So common substituents, we mentioned methyl in a previous video, so methane becomes methyl, ethane becomes ethyl, propane becomes protyl, butane becomes butyl. So you get that Y ending. Then you have isopropyl, where the group attaches to the second carbon instead of the end carbon. You have tertiary butyl. We've got almost like a neopentane, except you chop one of the methyls off. We call that tertiary butyl or T-butyl. Then you can have halogenated substituents on your alkanes: fluorine, chlorine, bromine, iodine, which becomes fluoro, chloro, bromo, iodo. And you would name and number the location of each of those substituents like you would the alkyl substituents. So these hydrocarbon or alkyl substituents have their endings changed to YL, where the O endings tend to be halogens. Your cyclic alkanes, you form a ring. They're named by adding the prefix cyclo in front of the name of alkane. So cyclopropane and cyclobutane are just 3 and 4 member rings, but they tend to be strained because the bond angles are less than the tetrahedral 109.5 degree bond angle. So there's some strain. So it's a little bit more difficult to form those, and particularly the propane. Cyclopropane, if you form it, is very reactive because of that. So here are some cycloalkanes. There's cyclohexane and cyclopentane and cyclopropane. Notice you've got a 6-member ring. Notice at each point there's a CH2 for each, or a lot of times, just to save writing, we draw just the geometric shape. So that is our line structure, where we assume there's a CH2 at each spot, unless there's substitution on the ring. And so for cyclohexane, we draw a hexagon. Cyclopentane, we draw a pentagon. Cyclopropane, we draw a triangle, the shape that goes with the number of positions on the ring. They are structural isomers with the corresponding alkene. For example, if we look at cyclopropane versus propene, they actually have the same formula, because propane is C3H8, but propene, you've got a double bond and you lose 2 hydrogens, so it's C3H6, which is also the formula for the cyclopropane. If we move back up, you can see there's a CH2 in each spot, so that'd be C3H6. Okay, so we're going to look at the names of some of these structures. And now to do that, find the longest chain. So the longest chain will be this. And if you just gone straight across, you would have been wrong, because that's 1, 2, 3, 4, but this is 1, 2, 3, 4, 5. So we're talking about a pentane. Now, there's a methyl group attached. Now, there's our friend methyl. What's the position? 1, 2, 3, 1, 2, 3. So it doesn't really matter. It's 3 from either side. So we're going to have a methyl group. and it's on position 3, so we're going to call that a 3-methyl pentane. Right, there's really nowhere to go on this one. It's a butane. Got halogenated substituents, and again, it doesn't matter which side, so it's a 2, 3. But there's 2 chlorine substituents, so we call it dichloro. And then indicate the position. So it's a 2, 3, and then you put a little dash between the number and the letter, dichlorobutane. Here we got a 6-member ring, so that is a cyclohexane. And I've got an ethyl group attached to it. So it's an ethyl cyclohexane. Now you say, well, what position? By default, it's in position 1, but since there's only one substituent on the ring, the number is not strictly necessary. Looking at the last one, we go 1, 2, 3, 4, 5, 6. Since these methyls are on carbon 2, it's not going to really matter. So we will just use this straight chain as our group. So now we number 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Now this is 2, 3, 5. This would be 2, 4, 5. So we're going to number this way: 1, 2, 3, 4, 5, 6. It gives our substituents the lowest possible collector number, and this substituent gets a lower number. So it's going to be hexane, and it's going to be trimethyl. And so it's going to be 2, 3, 5. So 2, 3, 5, trimethylhexane. Now we can do it the other way and look at drawing structures for those compounds based on the name. So if we got hexane, we got 1, 2, 3, 4, 5, 6. Where's the bromines? 2 and 4, so we're going to stick a bromine there and a bromine there. Then we just have to really fill in the octets, or up to 4 bonds, with hydrogen. So CH3, there's 3 bonds, so that's CH, CH2, CH, CH2, CH3. And we got an octane, so we're going to need 8. 1, 2, 3, 4, 5, 6, 7, 8. So it's 2,2-dimethyl 3-ethyl octane. So when it's 2, 2, that means the methyls are on the same carbon. And 3-ethyl. And that's not going to make it the longest chain. 1, 2, 3, 4, 5, 6, 7, 8. It's the same as this, but more substituents have the lowest number if we go this way. So we're going to say CH3, 9, CH, CH2, 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 CH3. And then cycloheptane, we're going to need a 7-member ring. 1, 2, 3, 4, 5, 6, 7. And so we'll just arbitrarily make this fluorine spot 1, 3, 5. And it's 1, 3, 5, because if I count the other way, it'd be 1, 4, and 6, and that would be a larger possible numbering. So we're always going to number in the way that gives it the smallest possible numbering. So that would give us some examples of some structures.